So, happy field day, everybody. This is June 27th, maybe 2001. The 2021. Sorry, still trying to think of the date. But so field day comes, and I'm really not much one to talk on the radio too much. But I figure, in the true spirit of field day, I'll go out and play radio stuff, and I always end up messing around with antennas. So I have some video clips that I've been making just in some crazy antenna woes and things I've been finding out, just putting antennas up and working on them. Mainly it's mobile antennas and the big debate between mag mount and not mag mount, and some of the things that I've found. I always thought that mag mounts weren't quite as good as direct through-hole mounts or NMO mounts, and well, I'll show you what I found, but I think I've changed my mind a little bit about it. But anyhow, something I did want to explain here that really drives antenna theory home, and it's probably something you all know and just overlook from time to time. But if you look up there at the wave, and I'm going to try and get everything into the picture. If you look up there at the wave, that's 25 megahertz. It's 1 volt peak to peak, and it's gonna be just going into a dummy load here in a second. But I have the oscilloscope hooked right to the output, and I'm going to zoom out a little bit so you can see what I've done here. All right, let's look, shall we? And it's funny because it really dawned on me when I was working on the TS940, when I was working on the signal attenuator, how effective this really is when AC and DC voltages or work is pretty similar until you start to get up into the RF ranges, and then everything's off from that point. But and I'll show you why I'm telling you that. Anyhow, I have the scope here. It's 25 megahertz. It's going out, and it goes up into the oscilloscope here. Here's the other end of the leads. As you can see, it's a 2 lead. Here's the other end. They're open. And just to show you why I'm showing you this is, if you have a direct short, let's just say you're working on your car, and somewhere along the line in your turn signal wiring you have a direct short. It blows the fuse, and no matter where you check, you have a direct short. So you get into that train of thinking, working on house wiring. Something blows a breaker. Anything in that line where the breaker's blown will indicate that there is a problem. Thing is, once you start getting up into the radio frequency range, so you're looking at the scope there, and I can't see how big the signal is, 3.32 volts it's saying. So here's our leads, and you can see they come straight from the signal generator. And you can see in the background the 25 megahertz signal. Watch. When I jumper these together, that barely changes. Barely changes. Kind of because this is acting as an antenna, and if you ever look at the what happens to the voltage and current ratio or relationship in an antenna, how it's basically a sine wave. And I'm willing to bet if we could extend this or shorten this to certain different lengths, we'd see more of a change or less of a change up there on the scope. But just to give you, for instance, and just because I want to have a little bit of mercy on my power supply or my generator there, right here in my hand I have a 8 ohm resistor, just anything. I just was looking for something that wouldn't quite be a direct short. I'm going to put that on, and for now I'm going to lay that down, and you can watch what happens to the voltage as I decrease in frequency. So let me go down. We're at 20, 17, 16, 15, 9 megahertz. I'm going to change this a little bit so that we can see. Why is it taking so long? There it is. Okay, that way we can still see the sine wave. So now we're at 4 megahertz. We're at, no, now we're at 0 megahertz, so we're at DC. Well, in DC you can see it goes away. So now let's go over, and we're now at 900 kilohertz. I'm going to turn this again so that you can kind of see. 900 kilohertz. And you can see the closer we get to DC, the more this behaves the way you would think it would. So we're at, what, we'll just say 100 kilohertz. So now I'm going to take my resistor off. And there you have it. And the further we get down there, and as you saw when we hit DC at the one point, so we'll go even further. So now we're down to 10 kilohertz. And our signal there is, oh, I think it's less than half a volt. I don't want to get my head in the way. I think it says 500 some millivolts. So it's around half a volt. Still have the resistor there. See when we unplug it now. And then as you get, the closer you get to DC, and we'll take it down, I'll just plug in 60 hertz because I'm tired of turning this. 60 hertz, and that's what you get when you have the direct short. Well, I guess I need to make that a little bit more like a sine wave so we can see it. There we go. So there's 60 hertz, and when I make it the direct short, let me grab on here. And now it's definitely picking up some hum just from everything being on down here, but you can see it's almost zero. So that's what you get. And then when you get down to DC, and that's where the voltage acts the way we would expect it would act. That if you had a short, no matter where it's at in the line, you wouldn't have a signal. So just keep that in mind anyhow when you're working with RF, that even if there's a short somewhere, the length of the line, or depending on where it's going to, the wave may interpret that almost like it does through an antenna, where it's relationship between voltage and current are different. You know how in a short you have max current but minimum voltage, because if you put a voltmeter at the short, you would show zero because it's at ground, provided it's a short to ground. But and that's where all your current will be going, is right there to the ground. So that's where your current would be max, your voltage would be zero. Then think of an open circuit here. An open circuit, two open wires, like from the battery. You put positive and negative, you have max voltage, but there's no current flow in between them other than when it's just using that little bit to power your meter. So you have max current, or max voltage, but minimum current. And that's kind of what happens, the properties all through a transmission line. Not so much the transmission line, but actually the radiator, like the antenna itself. Enough about me babbling on and on and on about things like that. So what I'm going to do is I'm going to just play a bunch of clips that I've compiled regarding messing with this antenna. And do I have a hypothesis yet? No, probably not. But I'm still kind of playing around and seeing what the best option that's going to work for me is. And a couple things, when you look at this, you're going to see that I have a toolbox in the back of my truck, and the toolbox, although it is bolted to the bed, it's mounted on the plastic rails. How good the ground connection actually is going to the truck itself from that toolbox, it's probably not that good. It's probably pretty high resistance. In fact, I think if I check it, I do have a different antenna hook there, so the ground from my VHF antenna, it actually comes in and attaches the VHF radio, and the VHF radio has ground, so there's one ground there. But I have tried tying different external grounds to the toolbox down to the frame just to see if it made any difference, and it didn't. I tried different types of coax, because the first thing I thought was, I must have some junk coax. I tried wrapping a couple winds around a toroid coil, the 240 by FT 240 43, thinking that maybe I had some common mode noises coming back down through the antenna, which it still may be something like that, and maybe my makeshift quick coil didn't. I think I put about 6 or 7 turns on it, but it had no effect whatsoever. But something to watch. So without further ado, I'll roll the rest of the stuff, and thanks for watching. I hope it's helpful for you and gives you an idea to go out and mess around with things. And if I get any updates, I will update as needed. Hello, it's Tim here again. So there's the subject right there, and basically what I want to look at is mounting an antenna for HF, and just see what kind of difference things make. As you can see, there's already 2 antennas back there on the toolbox, and what I want to see is what the difference is between a through-hole NMO mount and a magnetic NMO mount back there on the toolbox. I have a metal plate, even though it's an aluminum toolbox, I have a metal plate that I can put a magnet on. So we'll see what the difference is when I mount the same antenna that's in the NMO. We'll put it in the toolbox, see how that changes the frequency range. Then after that, I want to put the antenna right in the middle of the roof, because you know how HF, it really likes its ground plane, and we'll put that there. And the other thing I want to try is just see how the antenna beside it, if I remove that and put it back on, how that influences the antenna. I'm going to be using an Mfj Antenna Analyzer, not a radio, because I haven't even trimmed that antenna yet. To tell you the truth, I haven't really settled on a frequency, because I like to use it on 28.5, but I'm also a little bit into CB. I use that a little bit for the old 27 megahertz CB, so more than likely I'm going to end up cutting it for 28.5. But that antenna is a base loaded whip, so we'll see what happens when I try that. So stay tuned and enjoy the fun. Okay, try to cut the glare out for you. But that's the antenna in the NMO mount, back just the way I showed you before, nothing spectacular done to it. And we're getting somewhere in the neighborhood of 2, and that's 26.190, well, 26.187. You can see the impedance is bouncing a little bit, trying to make it as close to 50 as I can get it. So it's right around 2. So what I'm going to do now is first I'm going to unscrew the other antenna that's beside it, see how that changes things. Then after that, we're going to swap and put the magnetic mount on and see how that changes things. So hang on. Okay, now as you can see, it's the VHF antenna is removed. Okay, and then back in here at this, let's see what we can do. So I don't know. I don't really know that it changed too much, but there's always that question. Looks like the best we're getting right around there is around 26.260. So did it really change that much, or is it just in my fingers and adjusting? But the question was always, if you had another antenna close to it, how would it influence the SWR? So you can leave that to your own mind to try that. Let me put the magnetic mount on then, and we'll go from there. Okay, so there's the magnetic mount in all its glory, and you can hear Big Mouth over there barking. Okay, so there's the magnetic mount, and as you can see, we're already in the same area, but we're quite a bit higher. Let's just see what we can do to bring SWR down. Whoa, look at that. Would you look at that? Quite impressive. 1.2 with the mag mount. So what that tells me, one thing is I definitely have to go check on my to make sure there's not an issue with my NMO mount the other way. But that's a 26.892, so 26.9 roughly. And that is with the magnet mount, and again, like I said, it's behind the truck, so you know what kind of signal propagation that could possibly give you. So now I'm going to try and put that, well, first I want to plug the other antenna on and see if that changes anything. Then I'm going to put that antenna mount on the middle of the roof and see what we do then. Okay, trying to move again. We got the UHF or VHF antenna mounted right next to it again. It's probably about a foot away as it was before. Let's just see if it changes anything. About the same, so there you have it. That's how much influence you'll get out of having an antenna that close by. Now, I don't know about what kind of coupling you're going to get if you start transmitting through it and you have the other radio on, but generally I wouldn't have them both on at the same time. Okay, I'm going to stick it on the roof and see what that does to our frequency. Okay, it's a pretty big magnet that I'm using. So it has, hang on one second. Yeah, that magnet that I'm using is pretty big, and it has a 5 1/4 inch base. So it's hard to find a place up on the roof where you can put it. But anyhow, let's see. You can see where our SWR has changed a little bit. Whoa, look at that. Our frequency's gone down a little bit, but we're clear down to less than 1.2, 1.1. And we're close to 50 ohms. Just moving the coax around is changing our 50 ohms a little bit. But I want to first reevaluate that reading we got, because it was so high and made such a difference using the magnet mount. So we'll go back and take a look at that and see where we end up with. Okay, and there's again the lowest with the NMO, but I see the impedance is moving there a little bit. Could indicate that I have some coax issues, so I'm going to ohm that out with the ohm meter and check the coax, make sure that I don't have something going on there. It is some old coax, but should still be working. Okay, so what I did was I switched the mounts around, and I'm using the mount that was on the VHF now for the 10 meter mount. And I went the other way, switched them both. So there's a slight difference, but you can see the needle's still dancing. That I want to look into. But apparently that's going to happen there for some reason, but I don't know what that is indicating. That's what I want to look up. And the SWR is a little bit better. It'll drop down to about 1.6, but then we start to really drop down on our impedance. So to keep our impedance up around 50, the frequency is a little bit different. The SWR is a little bit higher, but the needle's still bouncing. But that could all be due to the fact different locations, even though they're kind of close to each other, but definitely different cable going back. The cable that's hooked up here is much older than the stuff that was going back, and it's not new. So, what have we learned? I don't know. I really don't. Alright, that is with the antenna sitting right at the corner on the driver's side here. No, good one, Oliver. No magnetic connection, just sitting there. Okay, with a slight couple changes, and I will show you 1-to-1 at 26.742. Let me put this guy back here like so and come back here. Now what I've done is mounted this directly to the box without the doohickey, without the plate there. But you'll notice there's a capacitor in parallel with the antenna. It's 100 picofarad. So I'll show you what happens when I take that 100 picofarad off. I'm going to have to pause this to do that. Okay, so same antenna setup. Now I'll probably have to go back and take the first measurement with it on this magnetic mount here, because I had to take the spring off because it was so close to that the spring was actually touching this. So of course that wouldn't work. But anyhow, let's see what the SWR and best frequency is now without the capacitor. Alright, nothing, I didn't touch anything over here. So it was 26,730, some 2.2. Let's just see if we can get that lower. Nope. So the frequency doesn't change much. The resonant frequency, as you can see, I went from 1.1 to 2.1 just by adding that capacitor in parallel. So is that taking the place of the capacitance that would be introduced if I were to use a mag mount as opposed to a direct mount? So I want to try that same mag mount antenna where it was, and I want to try it with without that spring on it. Alrighty, so there we have it. Oliver, leave that. It's going to eat the capacitor. What do we get? The best we get is 26,717, so around the same at 1.3, 1.4. And just for documentation purposes, I'll fall and crack my head open. Let's see now. There it is there. And as you can see, there's no magnetic coupling whatsoever. There you go. What does all this mean? Let's hash it out together. Yeah, so something else to document here. Let's see, but 26.774, and that's with the same mag mount on the roof. So it just kind of shows you that very interesting. Something else I want to add while we're here. So if you look here, another change I'll show you in a minute at 27,095. And lowest I can get around 1617, about the same thing, maybe a little worse. But you see the frequency changed, the resonant frequency, and I'll show you why. I don't know if you can see that, but I removed the red cap. Sorry, that was my finger. I was trying to see if I could show you the red cap. I removed that. And if you read this, that's a Fire Stick antenna. If you read the Fire Stick antenna or even watch their videos, they tell you, make sure you put the red cap on before you finish your adjustment. So just to show you, that's all I did was remove the red cap, and the resonant frequency changed by a good amount. So a couple more things here I wanted to document. I moved the antenna temporarily to the other side of the truck, and the readings are pretty much similar. Seems like it's a little better on this side, but I think there could be a lot of other things to consider. But anyhow, there we go with the resonant frequency being around 26,759, and it's showing 1:1, but this is saying a little bit worse, so it's somewhere in that area. And I'll show you where we've moved the antenna to. We're on the opposite side of the truck now. The cap is back on. The reason I did that was I wanted to just try some stuff. If I move the antenna obviously closer to the bed of the truck, or to the body of the truck, let's see what that does with the antenna. All right. Resonant frequency stayed about the same, but the match went up a little bit, 1 to 4. So let's see if I move it over to where my NMO jack is. So we'll put it right about there. just for even worse, I'll put it there. It's kind of like somewhere halfway in between everything. Let's see what that does to the match. All right, so now looks like we're about 1.6, somewhere in that area. So my question is, if I use the 100 peak capacitor on the NMO jack, can I get down to about this at 26,692? All right, we're fighting the darkness out here a little bit, but let's see, 26,650, and we're showing 1.3. It's about the best I can get it, and I'll show you what I have here. There it is there. And I'll show you what I have going down below. You can see, I don't know if you can see there, it sticks out like a sore thumb, that blue capacitor. That's the 100 picofarad capacitor. So, I mean, that just happened to be what I brought out and tried, and there was more to it than that I can explain later. But I may be able to get it lower. So I want to try one more thing and pull the cap off and see if that gets me closer to the CB range resonant frequency. And the reason I'm trying that is because if I keep screwing things up in the CB range and I cut it too short, well, then I'll be in the ham range. So I could use it on 10 meters. All right, so there's about mid-band on the CB, and without the infamous red cap on, 1.5. So it looks like it stays under the whole CB band with that. So now I want to try it with an SWR meter real quick on channel 1 and just see what we get. See how true we are to the Mfj Antenna Analyzer. And all I did was take the cap off anyhow, but I'll obviously have to trim the antenna if I want to stay in that range. Okay, so for whatever reason, this is channel 1. And I've already calibrated it. And it shows me a little bit worse than 2. Let's go up in the band here and just see if by any chance. So, sorry you can't see everything, but here's channel 10. I have to calibrate. I have to put the phone down to do this. Alright, so there's channel 10. Look at that SWR. Excuse me. Let's just try channel 40. Let's see, 39, 40. Alright, hang on, I gotta calibrate. Alright, look at 40, over 3, almost 3.5. So the question is, did adding that capacitor decrease my bandwidth? I don't know what you normally get out of one of these antennas. We're going to try the middle of the band real quick and be done. Alright, lastly, here goes channel 20. 20 is a little bit worse than 1.5. So, more things to think about. Alright, so what I really want to know is what the bandwidth is of this antenna, and it's the same antenna but using the Magmon stuck on the corner of the toolbox. I'll show you that in a minute, without the cap on, because that's the way I tried it on the other radio. So trying to cut the glare out of the SWR. We'll watch up here. I wanted to keep it below 3, and as you can see right at the frequency it's at, it's kind of bumping around. So here we go. Let's see. Oh, wrong way. So it looks like 26,782, and then I go all the way to 27,513. Okay, so that's the bandwidth from the antenna when it is on that mount. And again, like I said, no magnetic attraction there whatsoever. All right, so I'm going to try it back on the NMO mount that I had, and see what the bandwidth is here. Now that, remember, I have the 100 picofarad capacitor jumping, so I want to see if that has changed the bandwidth at all. Okay, now we're plugged back into the NMO, and you can see it's kind of bouncing around there. So around 26.9, and then let's see how far up we can go, and then get my finger out of the way there. Back too high. Two. 27. Oh, come on. We'll say 27.34, somewhere in that area. So I'll look over and calculate the bandwidth of that, which is pretty easy, but I don't remember the numbers. That's why I'm using the phone to record everything. I've probably done this test, I don't know if I said this before, 1 billion times, but I never wrote anything down or recorded, so it was every time it was kind of like I had to, it was like I had to remember what I did the day before, so every time it was like a new start. Excuse me, my nose is running a little bit here. All right, let me turn this off, and I think we've collected enough data here to now confuse ourselves even more. Thanks. All right, so what I came up with was with the NMO and the mag mounts, the ranges for an SWR of 3 or better was, with the NMO, was 26.9 to 27.34, and that's about a 440 kilohertz span or bandwidth, and that's with the NMO and the 100 picofarad capacitor. Now with the mag mount, 26.782 megahertz through 27.513 megahertz gives us about 731 kilohertz. That's on the mag mount. So you can see it's not quite 50% better, but it's better. Now the caveat to all this is the fact that trying to scroll or work that meter by hand is not as accurate. There was times when it was jumping up by more than a couple hertz at a time, and the reading was from, well, you saw it anything from 2.9 to 3.1 all the time. So this is kind of just a rough average of what I'm looking for, but it seems to me that could it be it's a different coax and everything? Sure, it can be any of those things. But what I'm looking at is, what am I going to get if I mount to that NMO versus putting a mag mount there? So one other thing I may want to try is I want to see if I change the capacitance, if I can get even lower. I forget what the best SWR I got with this was, but it was below 1.5, but maybe if I change the capacitance a little bit more, I might be able to get even lower. And if I'm starting from a lower point, that would give me a wider bandwidth to get from, basically to get from 1 to 3 is more frequency than it is to get from 1.5 to 3. So that may change too, but it also may narrow the bandwidth. So even though I'm traveling a further distance, it's doing it at a greater, basically the curve isn't so smooth. It's pretty sharp. There, that's the word I'm looking for. It's pretty sharp going up. So let me hang on one second. Let me look at one other thing. All right, so another thing is the whole CB band. If that would, you'd be cutting the antenna for that, for a 40 channel now, goes from 26,965 to 27,405, and that's a span of 440 kilohertz, which oddly enough, this is yielding. Now, you never really want to be operating that far away from a 1-to-1 ratio, but 1 to 3 is still acceptable, or 3 to 1 rather, is still acceptable. But you know, with only 4 watts and a marginal mobile antenna, you're gonna be looking at losing some transfer of power to the atmosphere. But it shouldn't hurt the radio. So let's put this all together, crunch some numbers, and see what we can come up with. Okay, I have 2 100 picofarad capacitors in series, which theoretically would make me around 50 picofarad, because remember, capacitors in series act just the opposite of resistors in series. So take a look at this. Mainly you're just watching the frequency, or the SWR. It never goes down below 2. Right about 2, that's it, in that range. So now I'm actually going to go in parallel, and that would make them, like, it would actually double it, so it'd be more like 200. So let's just see what happens then. All right, so here we go. When I double it, where's the darn knob? There we go. Yeah, I don't even come to 200 now. I'm sorry, I don't even come, well, 2.0. Pretty close, but no cigar. So let's just drop back to the 50 and reconfirm, or back to the 100 and just reconfirm with 100. All right, all back to where we were. So let's just confirm the 3.87. Yeah, we'll probably go 3. We'll go 3.8. See, that's what I mean, it's changing. 3.85 on one end. And 27.338 on the others. So, see the bandwidth change. That's what I mean. This isn't a real accurate test. It just kind of gives me a rule of thumb or an eyeball view, as opposed to if I was actually able to plot it. So, all right, let me shut this down again. All right, well, I know I probably have a face that's more cut out for radio, but I ran out of still shots to show you. So I hope you enjoyed and took something away from the antenna video. And maybe if you're putting your own antenna in your car or truck and running into the same issues I did, it'll be helpful for you. I hope it is. That's all I have. Thanks for watching, and see you on the next exciting episode of Tim Time Projects.